the course on medical biomaterials. Today we are going to talk about properties, the mechanical properties a biomaterial should have. It should have lot of mechanical properties depending upon the location of the material. For example, if you look at the human body, it contains 270 bones at birth and it reduces to 206 bones as you grow older, because certain bones get fused. So, the bones, for example, if you look at the humerus, if you look at the radius which is outside, if you look at the ulna which is inside the arms, then you have your hand and fingers. Then if you go to the feet, you have the femur, then lower fibula, tibia, and then the actual feet. Okay. So, there are many bones which undergo quite a lot of tension, which undergo quite a lot of compression, and after an orthopedic surgery, replacement of some bone or filling up of some defects, we are going to place biomaterial. It could be a metallic biomaterial, it could be a combination of metals and ceramics and so on. So, these materials should have the desired mechanical properties. So, that is very, very important. So, these materials will face either tension depending upon where it is placed material, or they may undergo compression depending upon where the biomaterial is placed. So, the biomaterial has to be tested for several mechanical properties, especially materials which are involved in the orthopedic. That is why there are metals used quite a lot in orthopedic situations like stainless steel 316L, titanium, then alloys and so on, actually, because these can take up a lot of load, especially if you look at these parts here, it is going to take up the load of the human being. So, they have to be quite strong. Okay. So, what are the mechanical properties? Compressive strength, tensile strength, bending strength, because many times, as you know, we keep bending our arms, our foot, our leg and so on. So, the material has to have that particular property. Flexural strength, again we are flexing some parts. Even if you take the heart valve, diaphragm heart valve, it keeps opening, closing so many thousands of times a day and for a very, very long period. So, they should have the enough strength. Then modulus, the modulus of elasticity, that is related to the stress and the strain. So, these are the mechanical properties the material has to have. It is not that all biomaterials should have this, but especially materials which are involved in orthopedic surgery have to have some of these properties depending upon where it is placed in the human body. So, elastic modulus, what is elastic modulus? This is the ratio of stress to strain. Okay. The most important, in fact the most difficult challenge is to have a material which has the elastic modulus of that of the bone. Bone has a very low elastic modulus, and we do not want very strong material like stainless steel actually, because that has very high elastic modulus. So, then came titanium, and then now they are looking at other alloys, so that you can keep on reducing the elastic modulus. Whereas 30-40 years back, the general feeling was to have material which are extremely high in elastic modulus, but they have realized that we should not have such material placed next to the bone, because the bone elastic modulus and the material elastic modulus will not match. So, most of the load will go on the material which has very high elastic modulus, and that is called stress shielding, and the bone will start losing its strength. Okay. So, there is a lot of research now being done looking at material which have very low elastic modulus. That is why ceramics and some of the oxides are coming into picture. They have a compressive strength, compressive elastic modulus matching with that of the bone. Okay. The next one is hardness. You need to have desirable hardness, because bone has certain hardness. So, it should have desirable hardness, but then it should not have too much hardness more than the bone, because if I am going to conduct a surgery keeping some material next to the bone, then it may penetrate the bone. So, it has to match, that is very important, hardness. Then comes fracture strength. So, what is the maximum stress the material can take up before it actually fractures? Fractures means breaks. So, that fracture strength is very, very important. Fracture toughness. What is the difference between strength and toughness? Suppose there is a crack, how the crack progresses, that is called fracture toughness, and especially this is very, very relevant in ceramic like material. Okay? It helps to evaluate the serviceability, performance and long term clinical success of a biomaterial. So, serviceability, long term use of the biomaterial. So, fracture strength is when the material will fracture, fracture toughness is if there is a crack, how it starts propagating. So, that tells you the toughness of the material. So, these are some of the properties that needs to. Then you have fatigue. Like I said, you have these diaphragm heart valves which opens, closes. So, this is called a repeated loading or cyclic loading. So, loading, unloading, loading, unloading. So, repeated tensile strength may be there or compressive strength. For example, if you see our foot, when you are walking, each foot undergoes a certain compressive force, and that is sort of repeated. There is a compressive force, and then when we lift the foot, the compressive force goes away. Then again when we place the foot on the ground, our whole body stands on it, so there is a compressive force. So, this is called repeated compressive stresses. So, the material, if it is placed in such areas, it should be able to take up that. That is called fatigue. So, the material may have good tensile strength, but because of the repeated compression, uncompression, compression, uncompression, or repeated elongation, stopping the elongation, repeat again elongation, the material may fail. That is called fatigue. Okay. You need to understand this diagram. This is called a stress strain diagram. For the next 1 or 2 classes, I am going to talk quite a lot of mechanical engineering, and you will come across these stress strain diagrams, stress, strain, modulus, compressive stress, shear stress, creep, and so on. Actually, all these are mechanical terminologies, and you need to understand this if you are planning to design material, that is biomaterial, which is going to undergo such forces and such extremes actually. Okay. Okay. So, what is this stress and what is this strain? Okay. So, stress is nothing but force by area. So, if I am applying a force, suppose I am pulling a rod of certain diameter, imagine I am pulling a rod of certain diameter, or I am compressing a rod of certain diameter. Okay. So, the force that is acting on it divided by the area, that gives you stress. Okay. You can have tensile stress, you can have compressive stress. How is it represented? What are the units? It is normally Newton per meter square. As you know, you must have studied in your school. Okay. You have the force always represented as Newton, and area, that is why meter square. So, Newton per meter square or 1 Newton per meter square is also called Pascal. Okay. So, you will come across this Newton per meter square, Pascal in the next few classes, especially when we talk about strength of materials. Okay. So, once more, tensile stress is force per area, generally it is represented as Newton per meter square or Pascal. What is strain? Strain is elongation divided by original length. So, if I have say 1 centimeter rod, I am pulling it because of some force, tensile force. So, the rod becomes 1.1 centimeter. So, from 1 centimeter it has become 1.1 centimeter. Then the strain is, it got elongated by 0.1 centimeter. So, 0.1 divided by original length is 1. So, strain is 0.1 by 1. Please note that strain has no units because you are dividing the elongation by original length, whereas stress has some unit. Okay, force by area. So, it is as Newton per meter square or it is represented as Pascal, do not forget that. Okay. So, in this axis we plot stress, in this axis we plot strain. Okay. So, as I keep increasing the stress, that means as I keep increasing the force, obviously the elongation is going to increase. So, my rod gets longer and longer, so strain also increases, okay, like this. Do you understand? Please understand this. This is called the elastic region. Why? Because once the force is removed, the material will come back to its original length. Okay. So, all materials have elastic region. Okay. This is called elastic region, understand. So, but then you can't keep on extending. So, at some point, that is called the yield point or yield elongation, okay, the material will not be elastic, it will go into a plastic region. That means, if I remove the stress or if I remove the force, it is not that material will come back to its original, because it has become little bit plastic. So, the first point is elastic and the second point is plastic. So, if I apply more, so the strain will keep on increasing and then ultimately it will break, okay, the material will break, that is called the ultimate strength. So, this is called the yield strength, this is called the ultimate strength. Yield strength is up to a certain strength, the material is in the elastic region. That means, if I remove the force, material will come back to its original dimension, whereas beyond that material will not come back to its original dimension, but it will not break. The breaking is here, that is point of rupture, that is called the ultimate strength. Okay. So, this is called the plastic region, this is called the elastic region. So, in this elastic region we can assume this line to be a straight line. So, stress and strain are connected by a linear relationship. Okay. So, stress is equal to slope into strain, that is in this region we can consider the whole relationship as a linear. So, the slope, so stress is equal to some slope into strain up to this, okay, that is the yield point, that is up to the elastic region. So, this is a very important picture. All materials will have some sort of a stress strain diagram, some of them will not show yield point, some of them will have different slopes, some of them will have different heights and so on, whether it is a stainless steel or a titanium or a plastic or a ceramic, okay. Everything will have some stress strain diagram and they will vary quite a lot. I am going to show you, and once you know the stress strain diagram, you can decide which type of material to use depending upon the application. Okay. Okay, so, the tensile strength, so the ultimate strength is here before the material actually breaks. Okay. Okay, so, the tensile strength, if you are talking about, is the maximum stress it can withstand without breaking. So, this is the elastic region, this is the plastic region. In the elastic region we can assume this line to be a straight line, linear. So, stress and strain are connected by a linear relation. So, stress is equal to slope into strain, and another important point is strain has no units because you are dividing elongation by original length, whereas stress has a unit because stress is equal to force by area. Force is represented as Newton. So, force by area is Newton per meter square, 1 Newton per meter square is 1 Pascal. Okay. So, this is a mathematical representation, epsilon delta is the change in the length or elongation divided by original length, stress is sigma, force by area, okay. And there is something called the Hooke's law, sigma is equal to E, capital E by epsilon. Okay. I told you in the previous graph, this is a straight line, so this is the slope, so stress and strain are related by that slope. So, that is what this Hooke's law is about. Sigma, that is the stress, is equal to E into epsilon, epsilon is your strain here. E is called the Young's modulus or modulus of elasticity. So, Hooke's law is valid only in the elastic region, please remember that. So, sigma has a unit like I told you in the previous, force by area. So, Newton by meter square or Pascal. Epsilon has no units because you are dividing the elongation by actual length. So, this is dimensionless. So, E will have the units of sigma. So, E will have units of Pascal, remember that. So, E is called the modulus of elasticity or Young's modulus. So, different materials have different types of stress strain diagram. So, here we are plotting epsilon, here we are plotting sigma. So, if you take steel, okay, it goes like this and like this, okay, sorry. So you have the yield point, you have the ultimate strength. So you have the yield point and you have the ultimate strength. Whereas if you look, so this is the elastic region, this is the plastic region. If you look at aluminum, it looks more smoother, it does not go like this, but because if you keep on extending aluminum, suddenly after some time it will become very plastic, you know. You can see that it gets extended and extended, and when you remove the force it will not come. Look at ceramic, it goes up and at some stress it just snaps, breaks, okay. So it does not go into a plastic. So ceramic does not have a plastic region, it is elastic only. So that is a big problem about ceramics, it cannot have very high tensile, it will just snap or it will break. So we do not use ceramic material when it is in the when it is undergoing tension. Generally most of the orthopedic implants, as you can see, they use steel or they use titanium, metals only they use. They will not use ceramics or inorganic material, because inorganic material will have a stress strain diagram like this. They will go up and at some place it will just break, it snaps, okay. So it will not go into the plastic region at all. So please look at this stress strain diagram, how different the materials are, okay. You can see very clearly the yield stress for steel, but the aluminum quickly changes from elastic to plastic. So polymers, if you take, the graph may go like this, much lower, okay, and so on actually. Axial stress is what we call, because we are talking about force on either side. Imagine this is the rod, A is the cross section, L is the length. So correspondingly, just like tensile, we can also have compression, especially if you look at foot, leg parts, because of the weight of the body, the material could be under compressive force, okay. Just like tension, you can have compressive forces also taking place into them. So the normal strain, once more, as I said, delta L by L naught, we can call L naught could be the original length, delta L is the extended length because I am applying a elongation, or delta L is the shortening of the original length because if you are applying a compression, okay. So epsilon is delta L by L naught, epsilon does not have a unit, okay. There is something called Poisson's ratio, you need to understand Poisson's ratio, which is the strain in the x axis, x direction, strain in the z direction, okay. So if you have a rod like that, okay, imagine you have a rod like this and of length L, okay. So we have z going like this and x going like that, okay. So when I am pulling that rod, the rod may change its length in this direction, as well as the rod may come down in that direction also, both are possible, right. So there will be a strain in the L direction, as well as there could be a strain in the W direction also, okay. So so if I have a rod, I pull it, the length may go delta L, but the diameter may go down, so both can happen, okay. That is called Poisson's ratio. That is why you have a negative here, because if one direction it elongates, in another direction it will get contracted, okay. So Poisson's ratio is also important, because imagine I have a metal implant which is fitted inside a hole, okay. Because of tension the metal implant gets elongated, but its diameter can shrink. So there could be a hole created, gap created, because its diameter has shrunk, okay. So if you have very high Poisson's ratio, you will be in trouble. So if there is a tension, the length gets elongated, but the diameter decreases, so there is a gap created between this biomaterial and rest of the bone. So that could be very deleterious. You could have infection taking place, and if you have say for example adhesive put into that, that adhesive could break or fail, all these can happen. If you look at teeth implant, they use quite a lot of these titanium screws, Okay, these titanium screws are nicely fitted into the jaw, and if there is a tension on this titanium, if it gets elongated, there could be gap created between the jaw and the metal. So, this gap could lead into accumulation of bacteria and so on actually. So, we need to understand what is the Poisson's ratio for the material also. So, we would like to have very minimum changes in their dimensions during tension or compression. Okay. So, Poisson's ratio is also very important. Let us look at a problem. Problems are very important because problems give you an idea about the concepts that I am going to discuss. So, we will try to do as many problems also during the course. So, we have a metal guide wire. You must have heard of guide wire. These guide wires are used quite a lot, especially when they place urethral stents inside the body or cardiovascular stents inside the body. These guide wires are made up of stainless steel or nickel titanium. So, they actually guide the material inside through the artery or through veins so that the surgeon can place the material at the desired place, and he or she will be looking at the location using certain visual devices. So, a metal guide wire is 2.5 mm dia and it is 2 meter long. Okay, 2 meter means about 6 feet long. When a force of 12 Newton is applied, forces I said we will always use term Newton during a surgery, it stretches by 0.3 mm. Okay. Determine the stress in the wire. So, we are looking at elastic. Determine the strain in the wire, determine the modulus of the wire. Okay, stress, how do you calculate? Stress is nothing but force by area. Force is given as 12 Newton, diameter is given here. So, area is pi d square by 4, you must have studied in your school long time back. So, stress is that. Area is equal to pi into diameter square by 4, pi into 2.5 square by 4, that comes to 4.9 millimeter square, force is 12 divided by 4. So, you get sigma, that is the stress 2.44 Newton per millimeter square. Strain is elongation divided by original length. Strain has no units. So, elongation is 0.3 mm and original length is 2 meter. So, 0.3 by 2000, do not forget 1 meter is equal to 1000 millimeter. So, you need to convert that. So, 0.3 divided by 2000, there are no units for strain. So, 0.00015. What is the modulus? Especially if it is in the elastic region, the modulus is given by stress by strain, simple. So, stress is given here, strain is given here. Okay. So, we use the Hooke's law, stress is equal to strain into modulus. So, modulus is equal to stress by strain. Okay. Simple. Now, we need to so 2.44 divided by 0.00000. So, there is Newton per millimeter square. As I said, the units of modulus or Young's modulus will be same as that of force. Now, 1000 Newton per millimeter square is 1 gigapascal. This gigapascal, megapascal means 10 power 6 pascal, gigapascal means 10 power 9 pascals. So, you need to remember all these. So, 1 gigapascal is 1000. So, if I divide by 1000, okay, I will get 16.26 gigapascals. So, the modulus is given by 16.26. So, you need to remember this conversion factor also. 1 gigapascal is equal to 1000 Newton per millimeter square. Okay. And 1 megapascal is equal to 1 Newton per millimeter square. Okay. Let us look at another problem. A stainless steel metal implant of diameter 2 millimeter and length 20 millimeter is placed inside which undergoes a tensile force of 10 Newton. Estimate the change in length it undergoes, modulus is 200 gigapascal. As I said the previous slide, 1 gigapascal is 1000 Newton per millimeter square. So, 200 means multiply by 1000, so many Newton per millimeter square. Okay. So, the force is given, diameter is given, force by area will give you the stress. Okay. The modulus is given. So, from there we can calculate strain. original length is 20 millimeter. So, from there we can calculate what is the change in length, that is delta L, understood. Okay. So, diameter is 2 millimeter, length is 20 millimeter. So, cross sectional area pi d square by 4. So, pi into 2 square by 4, 2 square is 4. So, pi by 4 by 4, 4 and 4 gets cancelled. So, cross sectional area is 3.14 millimeter square. So, please remember we need to maintain the units very correctly. Force is equal to okay, there is a mistake here. So, it is not 10 Newton, we will assume it as 100 Newton. Okay. Force is equal to 100 Newton, force is equal to 100 Newton. So, okay. So, stress is equal to force by area. So, 100 divided by 3, 100 divided by 3 will be 31.83 Newton per mm square, we use the same units. Okay. So, stress is equal to modulus into strain. So, stress divided by modulus will give me the strain. Okay. Stress divided by modulus will give me the strain. Okay. 31.83 divided by 200,000. Okay. Stress is 31.83, modulus is 200,000. So, 200 gigapascal is 200,000. So, that comes to 1.59 10 power minus 4. Now, elongation delta L is equal to L in length, original length into strain. Okay. So, strain is this, original length is 20 mm. So, multiplied by 20, this will be in millimeter because the original length is in 20 millimeter. Understand this problem. So, the diameter is given, length is given. So, force is 100 Newton, cross sectional area is pi d square by 4, stress is equal to force by area 31.83 Newton per millimeter square. Strain is equal to stress by modulus, modulus is 200 gigapascal, which is 200,000 Newton per millimeter square. Strain is equal to stress by E. So, 31.83 divided by 200,000. So, this comes to 1.59 10 power minus 4. There is no units so far because stress and modulus have same units. Then delta L, that is the elongation, is given by length into strain. Okay. Strain is this, original length is 20. So, you multiply this by 20, it becomes 0.00318. So, the length has increased okay, by 0.00318, understand, millimeters. Now, look at the same similar situation, okay, but the modulus has changed. Okay. So, originally I used a stainless steel metal implant, now I am using a titanium metal implant. Titanium has lower modulus, 100 gigapascal, otherwise it is the same 2 millimeter diameter and 20 millimeter is the length. It undergoes 100 Newton, oh sorry, this also undergoes 100 Newton per meter square, sorry 100 Newton tensile force. So, in the previous one it is a stainless steel implant with a modulus of 200 gigapascal. Here okay, in this particular case it is a titanium implant with a modulus of 100 gigapascal. So, what is the change in length? Same way we have the diameter is 2 mm, length is 20 mm, cross sectional area is pi d square by 4 3.1, force is equal to 100 Newton, 100 Newton. So, stress is equal to force by area. So, 100 okay, divided by 3.1. So, 31.83 Newton per millimeter square. Okay. Then strain is given by stress by modulus, sorry, stress by modulus. So, 31.83, here the modulus is 100,000, in the previous case is 200,000. So, we get 31.8 into 10 power minus 4. Increase in length is equal to original length into strain, original length is 20 mm. So, the increase is 0.00636 mm. Did you notice that when I use a stainless steel implant which has got a modulus of 200 gigapascal, applying same, if you have the same diameter, same length, same force, I got 0.003 approximately. And when I use a titanium implant which has got 100 as its modulus of elasticity or Young's modulus, the increase in length is 0.0063. So, it gets elongated much more. okay, than the previous one. Okay. So, you think it is not a problem, but it is actually a problem. Imagine I have a biomaterial designed which has got stainless steel and titanium. Okay. So, it is a biomaterial which contains stainless steel and titanium. I keep it inside the human body, and it is undergoing say a tension, okay, of say 100 Newton. It is undergoing a tension of 100 Newton, but it is a mixed biomaterial which has got both stainless steel and titanium together. So, one of them will undergo 0.003 mm elongation, another one will undergo 0.006 elongation. You are in big trouble, right? Stainless steel will undergo 0.003 elongation because it has got higher modulus 200 okay, whereas gigapascal, whereas titanium has 100 gigapascal as its modulus. So, it will undergo 0.00636. So, there is a difference in which these two materials will elongate, although this is a single biomaterial which contains both these. Okay. So, this difference is 0.003 if I subtract this, or almost 3.18 microns. So, if I have a biomaterial which is made up of a small rod of stainless steel and a rod of titanium, and I place it say suppose I fuse it on the top here and the top here, and I place it inside the body, and that particular material is undergoing a tension. Although the tension is constant, titanium will get elongated slightly more than the stainless steel, and this difference could be 3 microns. So, this biomaterial is in big trouble. So, the most important lesson from this is when I am having using different materials and prepare a biomaterial, if the modulus do not match and if the material is undergoing a tension, each of these materials may have different elongation. This can happen in compression also, each of the material will have different compression or elongation. Okay. So, the whole biomaterial could fail. So, there has to be a match of the tensile properties, especially if they face these type of axial strains or axial stresses or axial compressions. Okay. If they are not going to face this type of mechanical forces, then it does not matter, but if they are going to be placed inside, for example, in the human body and it is facing a compressive force or a tensile force, and I have different materials, the modulus of has to be modulus of elasticity, or the Young's modulus has to be same, otherwise their elongations may differ. So, one material may have a slightly longer elongation than the other, and this may lead into the failure of the entire material. Okay. So, we shall continue more on these mechanical properties in the next class also. Thank you very much.